Okay, so what is a confidence interval? A confidence interval is simply an estimate of an unknown population value using a sample. So it is a range defined by a point estimate, like the sample mean, plus minus a margin of error. And it always includes a confidence level or probability of actually including the population value that you're trying to estimate. Because remember, if we don't have all the population data, we can never be 100% certain. That's just statistics for you. So let's look at the employability scores from students entering our master's program. From the sample of 95 students that we have, we can estimate a mean employability score of 239.9. But we want to look beyond those 95 students and infer the average employability scores that we can expect from future enrollees in the program. And the good news is that from the central limit theorem, we know that the sample means are normally distributed around this unknown population mean. So let me draw this same sampling distribution of the mean to the side here, and let's think about our sample mean in this context. Remember, we don't know the population mean, we're trying to estimate it. So the sample mean could have fallen right here. In fact, it's quite likely since the sample means are concentrated around the population mean, but it could have also fallen right here for all we know, or here, or all the way over here. We'll never know for sure. So what can we do? Well, 239.9 is our point estimate, but it's unreliable. So we need to add a margin of error on either side to increase our probability of including the population mean in our estimate. And remember, if someone says probability from now on, you say area under the curve. So let's say that we want this probability right here of including the population mean in our confidence interval. Well, this area is known as the confidence level. And the distance between the mean and the bounds of this area is the margin of error. So we can add that margin of error to both sides of our point estimate, and we have our confidence interval. So if I apply that to all of my examples here, the confidence interval is exactly the same. It's our point estimate of 239.9 plus minus the margin of error. I'm just illustrating different possible scenarios. Since again, we don't know what the population mean actually is. We don't know what that orange line is. But the important part here, the key takeaway, is that we're more likely to obtain a sample that fits either one of the first three scenarios, since they are closer to the center of the sampling distribution. And you'll notice that for all three, the interval actually includes the population mean. But it's still possible to obtain a sample that fits the last scenario and that doesn't include the population mean. It's just not as probable. So that's what a confidence interval is in a nutshell, but I'll go into further details on the components in the next lectures. Alright, let's dig a little deeper into the confidence level. The confidence level represents the probability that your confident interval will include the population parameter that you're trying to estimate. And it's established by alpha, which is 1 or 100% minus the confidence level. Now, typical alpha values are 0.1, 0.05, and 0.01. You'll see these all over statistics textbooks and courses. But you should know that you can use any value between 0 and 1 that you like, and you actually shouldn't just arbitrarily pick one of the standard numbers. I will, however, if you forgive me, illustrate those three standard numbers right here. So an alpha of 0.1 represents a confidence level of 90%, in which you leave out the 5% of error at each tail, which is really just alpha divided by 2. Now an alpha of 0.05 represents a confidence level of 95%, and an alpha of 0.01 represents a confidence level of 99%. And before you think, well, why wouldn't I just go with the highest confidence level? Don't I want to be almost certain of my estimate? You could, but if you remember from the last lecture, the width of the area here is actually the width of the confidence interval. So as you increase the confidence level, the confidence interval also increases, it gets bigger. And that's why it's so important to take time to establish an accepted probability of error, or accepted probability of your estimate not including the population value, in favor of a narrower interval. And this will vary, of course, depending on each individual scenario. Okay, so by this point we have a point estimate from our sample and we've established a confidence level. So time to calculate the margin of error. The margin of error represents the value to add to each side of your sample statistic or point estimate to generate the confidence interval for your population parameter. And the size of the margin of error is determined by two things: the confidence level and the standard error. So if we go back to our employability example, we have this information at our disposal and we want to calculate the margin of error from this sample with a 95% confidence level. Now, you might be looking at this and thinking, wait, I get that we know the sample mean, the sample size, and we've established an alpha of 0.05, but where did that sigma value come from? So I do have to clarify that for this example, we're assuming that we know the standard deviation of the population, since we need it to know the width of our sampling distribution of the mean. Knowing this value, though, won't always be the case, and we'll cover those scenarios as well, so don't worry about that for now. Let's just continue with this example. So if we want to calculate the confidence interval, then we can use this formula, which seems unfortunate, but it's actually quite simple. We have the point estimate first, which is our x-bar, or sample mean, and let's just plug that into our formula, plus minus the margin of error, which is all of this. Now the first part right here is the z-score that the confidence level represents, also known as the critical value. So if we look at the standard normal distribution, or z-distribution, and add that confidence level of 95%, what we want to know is, what's the z-score at the edge of the area here? In other words, how many standard deviations away from the population mean does my confidence level allow my sample mean to be? That's what this number will represent. Now, to get this number traditionally, you'd have to look up values in this weird matrix type t-table, and you can still do that, but we don't need that here. We have Excel. And guess what? We know how to calculate this number already. Let me reframe the problem to solve to see if you can figure it out. We need to find the z-score at a given cumulative probability. Does any formula ring a bell? It's the norm.s.im function. And this right here is just the cumulative probability up to alpha divided by 2. That's where the formula gets the z underscore alpha divided by 2 from. Now this is going to return a value of negative 1.96, which is correct, but adding and subtracting a negative number is a little bit confusing. So a lot of the time you'll see this instead, which is just the cumulative probability of 1 minus alpha, or from negative infinity all the way up to the end of our area on the right here, which does get us the same z-score. It's just positive and easier to work with or think about. So that's one component of the margin of error. Let's go ahead and plug that value into our formula. But the other, as we can see from our bullet here, is the standard error, or the standard deviation of the sample means. And if you think about it, it makes a lot of sense. We know how many standard deviations away from the population mean we're allowing the sample mean to be based on our confidence level. All that's left is to know what the value of a standard deviation actually is. And we've seen how to calculate that already, and we can see it in the formula. It's just going to be the standard deviation of our population divided by the square root of our sample size, in this case 9.23. So let's plug that into our confidence level formula, and we get a margin of error of 18.09. And just like that, we have our confidence interval. So we can now say that we're 95% confident that the average employability scores of our MBA students, past and present, at the beginning of the program will be of 239.9, give or take 18.09. In other words, roughly from 222 up to 258. Which does also mean, of course, that there's a 5% chance that the real value is actually outside of that interval. Alright, it's been a while since we fired up the Excel statistics workbook with all of the foundations that we had to lay out on, the central limit theorem and confidence intervals. But we are back, and we're going to go to the first link under the confidence intervals section. So let's click on that. And we want to know what mean employability score we can expect from our future graduates with 90% confidence. And you will see that, again, we are assuming that we know the standard deviation of the population. So let's calculate our sample statistics to begin. For the sample size, we can use a count. And for the mean, we can use the average function. So this value of 289.3 is our point estimate, or x-bar. Now we need to calculate the margin of error. So to do that, let's start with setting a confidence level, which has already been stated here, so 90%. Our level of alpha is going to be equal to 1 minus this confidence level. And alpha divided by 2 is, well, alpha divided by 2, which in this case is 0.05 or 5%. Now, for the critical value, remember, we need the z-score at either alpha divided by 2. So let's do that first. Norm.s.inv of alpha divided by 2. And that's going to get us the negative value. We could also do the z-score at 1 minus alpha divided by 2, which will get us the same value, just positive. So let's use that one. And this is going to represent a number of standard deviations away from the mean. Now let's calculate the value for a standard deviation, which for a distribution of sample means is the standard error. So to calculate that, let's grab the standard deviation of our population and divide by the square root of our sample size. We get a standard error of 9.23. And to get the margin of error, we just multiply the standard deviation of our sample means by the number of standard deviations that will allow our sample mean to deviate from the population mean. Press enter. And then to get the limits for our confidence interval, we can grab our point estimate, subtract the margin of error, and then grab the point estimate and add the margin of error. And I selected the wrong cell here. But there we go. We can now state with 90% confidence that graduates from our program will achieve employability scores between 274 and 304 on average. Alright, so we just saw the longhand way of calculating the margin of error, if we want to call it that, and I did it so that we could see how each of the components in the formula plays their part on the end result. But it turns out that there's an Excel function that lets us do it all in one pass. So the confidence.norm function returns the margin of error for a specified confidence level and a standard error. So all we need to do is specify the alpha for the confidence level and the standard deviation of the population and sample size for the standard error. And if we look at this same example from the previous slides, you'll see that we've got the employability before sample, we've got our sample mean, our sample size, our population standard deviation, and our alpha value. And if we just plug all those into our confidence.norm formula, we get that same exact margin of error from the previous example. So now let's just quickly jump back into Excel so that we can do the same thing ourselves. Here in Excel, I'm going to actually jump back into the link from the previous lecture. And all I want to do is replace this margin of error that's using all these values with the confidence.norm function. Alpha is going to be 10%. Standard deviation of the population is 90. And the sample size is 95. Close that, and we get the same exact value and the same exact confidence interval. And we can actually delete all these, and we get the same result. I'm just going to undo, and there you go. Okay, time for an assignment on confidence intervals. Nick Normal is back, and he still wants to get some data from you on student salaries. So here's his message. I know you said our salary data doesn't follow a normal distribution, but I just wanted to try to see if you can produce some sort of expected annual salary from our graduates. I just read a survey online where they found that the average salary for recent MBA graduates in the US is $101,000. And it also said something about the standard deviation being $76,000, in case that means anything to you. Okay, so it actually does mean something to us. Now we have the population standard deviation of annual salaries for MBA graduates in the USA, and I do think that we're safe to assume that our students are a part of that population. So what we need to do now is calculate the mean and the sample size from the sample of graduates, set a confidence level, calculate the margin of error, and set the limits for the confidence interval. So get to work.